Swayam Prabha. Digital India. Educated India.
Now, I am going to describe a prototype algorithm. A prototype algorithm is the basic idea. So, I am now going to talk about a randomized algorithm for obtaining a fixed rank approximation. So, let A be a m by n matrix, let K be a target rank, let P be a oversampling parameter, which is a small integer which is between 5 and 10. I am going to now construct Q as m by k plus p. That is the output. This is the output I want. The input is matrix A, the rank K, and the oversampling parameter. K is given to you. You fix P a priori. Matrix A is given. I want to be able to output a matrix m by k plus p. Now, please understand. Originally, we thought we wanted only m by k. But because we realized the error throws the vectors out of the range of B, I would like to be able to capture as much as possible. So, if P is equal to n minus k, it captures everything, but n minus k may be very large. So, I am going to approximate n minus k by P. P is the order of 10, no more than 10. So, how does the algorithm work? Draw n by k plus b random matrix omega. What is that? I have a space Rm. In this space, I am going to pick randomly how many samples? K plus b sample size. Each of these samples are going to be mapped in here, Rn. So, here again k plus b samples come in. Each of the k plus b samples in here is the image under A. So, I am representing these k plus b as in the form of a matrix. The columns are k plus b. So, 1, 2 all the way up to k plus b. These are the vectors. Please understand, these are the vectors. So, this is equal to n by k plus p. I am sorry, m by k plus p. Each vector is in Rn. So, I have y is equal to a sigma. So, y is k plus b vectors that are output. I am now going to orthogonalize the columns of y, which is qr. And once I have orthogonalized y by a qr decomposition, you know q is the matrix of interest to us, mu is the k by t matrix. So, this is the basis for the range of A. And this is done by Gram-Schmidt approach. There is also an equivalent algorithm called Householder's algorithm, which I have not talked about. There is also another transformation which is called Given's rotation. So, this orthogonalization can be done by one of standard method. I have illustrated the Gram-Schmidt algorithm, at least one method you know. At least one method you know. So, we have now talked about the implementation of stage 1. I hope you are all with me now. The randomization comes from sampling. You remember, sampling based ideas is one way to be able to implement randomization. I have now a formal method for being able to capture a large fraction of the action of A in the range Rn by capturing the subspace of dimension k plus p, where k is the desired rank and p is the oversampling parameter. The oversampling parameter is meant to capture the information that leaked outside the subspace of dimension k. Performance analysis of this algorithm, that leads to the first theorem in this area. Many of these theorems I do not prove necessarily. I want you to understand these proofs, these theorems gives you performance guarantees of this algorithm. So, A is m by n, select a target rank k, m greater than equal k greater than equal to 2, and the oversized parameter k greater than equal to 2, and k plus p is less than the minimum of m and n, is minimum of m and n. If it is equal to the minimum of m and n, there will be a full rank. There is no point in asking what a full rank, because I do know the input matrix X has signal and noise. If the input matrix has signal and noise, the singular value spectrum will decrease very fast. All these are the basic ideas on which the whole entirety of the algorithm is based on, is built on. Now, execute the prototype algorithm. Now, I would like to be able to describe the way in which I am going to generate my random vectors. You remember the random vectors y's, random vectors w's. W is the random vector in the original space. N is the map. N is the map. So, omega ij, these are IID random variables in the each omega ij is each ij is standard normal. I hope you are with me now. So, you generate the elements of sigma ij as sigma ij are IID from normal 0 1. So, you generate the random vectors from whose components are IID in standard normal. This is very similar to what we did in Johnson-Renderstraus algorithm to create the random projection matrix. Here I do not use this as a projection matrix, but this is a sample from the range. To get a sample from the range, I am picking sample from the domain and looking at their images in the range. So, once I have omega, then I have y. So, omega to y using the transformation A, from y to q using QR transformation. So, this q is m by k plus p. This q is m by k plus p. So, that is the pathway. So, this q is the one that I am interested in stage 1. Instead of being m by k, this is m by k plus p, and we know the reason. So, what is the performance guarantee? It can be shown that the expected value of the error in the approximating A by rank q plus k, this is the random matrix. Why this random matrix? The elements of omega are random, the elements of y are random, the elements of q are random. Even though the procedure to obtain q from y are deterministic, if I am going to process a random input, the output is random. So, q is random. Because of this, the error is random. So, I am going to have to take the expectation of this error, the expected value of the error. The expectation is over the randomness of the matrix omega, sampling the original space. It can be shown this error is no more than the upper bound given in here. Look at this now. Sigma k plus 1 is the k plus 1 singular value of the given the original given matrix A. If it were to be a PCA, we can achieve the actual upper bound for the norm of the difference between A and approximation, which is proportional to, which is equal to sigma k plus 1. Here we are going to get a constant multiple of sigma k plus 1. So, sigma k plus 1 is the smallest possible error achievable, but in this particular case, since we are not using PCA, I can get a result which is similar to that, except that there is a multiplying constant. What is that constant? The constant is 1 plus 4 times square root of k plus b divided by p minus 1 times square root of the minimum of m and n. First, you need to understand the impact of the statement of the theorem. The impact of the statement of the theorem essentially tells you I can essentially bound the expected value. Now, please remember, now we have done measure concentration. What does the measure concentration tells you? In large dimension, the properties of random variables are concentrated around the mean. So, if I can have bounds in the expected value, we can have bounds in the moments, I can also have bounds on the tails. So, everything jives very well in here. So, this tells you the quality of approximation that can be guaranteed using a fixed rank approximation. This is known as sharper than the deterministic analog based on the RRQR algorithm of GNU and Eisenstadt in 1996. So, in 1996, GNU and Eisenstadt, they proved a result for randomized approximation, and they proved a bound which I am not going to deal with it right now, but I want to tell you this bound is sharper than the deterministic analog based on the RRQR algorithm. So, this essentially tells you that this result is an improvement over an existing result. Thanks to the measure concentration, if the expected value is bounded, this is the random event, the norm of the random variable itself I can bound, and please understand, one simple way to think of it is Markov inequality. If the expected value is finite and the error, the norm of the error is a positive quantity, I can simply apply Markov inequality to get a tail bound. So, that tells you then the probability of this error, norm of the error, is less than this quantity. The probability that, you can think of this as the probability that this event happens is at least 1 minus 6 times p to the power of minus p. So, what does it mean? 1 minus 6 times p to the power of minus p, that this is equal to 6 over p to the power of p. If p is 5, 5 to the power of 5, 6 over pi to the power of 5 is very small. Therefore, with a probability at least 1 minus, so that is a very large quantity, very close to 1. So, with a probability very close to 1, this error will be bounded. That means this essentially tells you the probability measure is concentrated. So, this is the concentration inequality, and so here I can decide the value of p. If p is 1, this is 1 minus x, does not make any sense. So, what is the p that will help you to make this number very close to 1? The larger the p is better. So, what is the least possible value of p that will make this number as close to 1 as possible? One such choice is p is equal to 5. You can choose p is equal to 10 too, that will be even better. So, for small values of p between 5 and 10, using this approach, given a rank k and a oversampling parameter P, I can approximate A to a K plus P rank matrix that essentially captures the action of A. If I can capture the action of A, I understand A. So that's the idea here. I am trying to capture the action of A. Some historical facts. Column selection. For every A m by n contains a C with k columns such that C plus C plus, C times C plus, you remember C plus is the generalized inverse of C. We have talked about generalized inverse H plus in the context of least squares. So, you already know H plus is a projection. So, what is this? I am talking about existence. Given a matrix A, there exists a collection of columns using which I can obtain a K rank approximation. So, that is a kind of an existence result I am talking about. So, existence for column selection. So, if I give an A, it contains a matrix C with k columns. So, the columns come from A itself such that the projection of A onto the subspace spanned by the columns of C, A minus that projected matrix, the norm of the error is no more than the right hand side. And what is AK? AK is the best rank approximation. What is the best K rank approximation to A? That is given by the PCA. So, this we already know from PCA. This is the multiplying constant coefficient. It can be shown given any matrix there exists a set of k columns. The submatrix consisting of these k columns is such that the projected value of A, the error in the projection, is no more than a constant multiple of the best error. If AK is the best K rank approximation, A minus ASK is the least error possible. So, the error in this approximation that is given by the column selection is no more than a constant multiple of the best result, the best K rank approximation. To do the best K rank approximation, you have to do the general SVD on the whole matrix. Now, we did not do a general SVD on the whole matrix, we did an SVD on the reduced matrix. So, the reduced matrix is going to provide an approximation. So, this relates to the existence of quality approximation when we try to seek a subset of columns of A to get a K rank approximation. This was done in 1964 by this existence result. This is called Auerbach theorem. This was done in Mathematical Proceedings of Cambridge Philosophical Society. So, much of the basis rests on this fundamental theorem that was enunciated in 1964. So, this essentially tells you that exists column, there exist k columns. So, this existence theorem essentially tells you there exist k columns using which I can get a reasonably good K rank approximation. The error in the approximation is only related to the best K rank approximation. So, this relates to how to find the columns. Please understand there are n columns. I am supposed to find k subset of n columns. There is nck ways in which the subset can be selected. There is no efficient algorithm known for this except for exhaustive enumeration. So, in other words, if I have if n is 5, if k is 3, I have to pick different subsets of 3 columns. Different subsets of 3 columns can be obtained in 3 ways, which is factorial 5 divided by factorial 3 times factorial 2. So, which is equal to 1 times 2 times 3 times 4 times 5 times 1 times 2 times 3, 1 times 2, these two get cancelled, this is 2, which is equal to 10 possible ways. So, when n is 5, k is 3, there are at least 10 different subsets of 3 columns out of 5 columns. Now, think of it now, when n is 10k, 10,000, if n is 10 to the power of 3 and k is 100, the number of possible ways of picking 100 columns out of 10,000 columns, that is a very large number. There is no clever algorithm except exhausting all possibilities. So, trying to find the best set of k columns that satisfy that inequality is computationally very demanding. Such problems in computer science are termed as NP hard. It is a very technical term. I am not going to the details of the definition of NP hard. Those of you who are interested in getting a good feel for that, you can refer to any standard textbook on algorithm analysis, or you can also refer to Wikipedia for a very good definition. Wikipedia has a very nice treatment of NP, the definition and examples of NP hard problems, NP complete problems. These are examples of the hardest problems in computer science. The efficient deterministic algorithm, which is RRQR method, which I talked to you about by GU and Eisenstadt, will achieve this above bound in 8. What is this bound in 8? That is the bound in 8. That means the error in the approximation is bounded above by a constant multiple of the optimal error. So, GU and Eisenstadt, falling back on the existence result, they proved a deterministic method for achieving that bound. Now, using this framework, now we are going to look for randomized algorithm for a fixed rank approximation. So, what is that we are seeking? We are seeking a matrix Q such that QQ transpose A approximates A in the sense of a norm, such that this error is no more than the best error in the best approximation. Error in the best approximation. Why? How do I say best approximation? Let X be a matrix of rank at most k. Among all matrices X with this property, what is the X for which the error in the approximation is minimum? So, this is the best error in the best rank approximation. I would like to be able to find a randomized algorithm that can achieve this. So, you can see historical perspective. In 1960s, somebody proved the existence of a subset of k columns. It was soon realized that subset of selection is a computationally difficult problem. The paper by GU and Eisenstadt gave a good column selection algorithm that can achieve a constant multiple of the best bound. Now, we are going to seek a randomized algorithm to achieve similar results. This approach uses sampling probabilities, please understand. So, I have to select the columns. What is one way to select the thing is by random sampling, as we already talked about and illustrated the power of the random sampling by the SVD idea that we already talked about. Now, please understand, why are we interested in column selection from there random sampling to column sampling? Because the range space is simply linear combination of the columns of A. So, I would like to be able to find the best subset of k columns that can approximate the subspace I am seeking. So, the whole question is, how do you select columns? How do you randomly select k columns out of n columns to be able to build this matrix Q that can approximate the range space of A? So, I want you to think there are lots of interesting ideas related to each other. We presented a general prototype algorithm. We demonstrated the power of the prototype idea by talking about how do I get an approximate SVD for a given matrix. With that on hand, we then looked at the problem of approximating the range space. Range space is simply linear combinations of the columns of A. So, I should be able to attack the problem of approximating the range space by simply selecting the columns of A. This problem is NP hard. I am going to get an approximation to an NP hard problem. I am using a randomized approach to this selection problem, column selection problem. So, there I picked the vectors W in the space Rm and looked at the map. That is one way. Here I am given a matrix, I am going to pick a subset of k columns, and how do I pick the subset of k columns so that I can capture the action of those columns to approximate the range space. So, sampling means I need to be able to specify the sampling distribution. So, there are two ways of sampling. One is called uniform sampling. So, if I have n columns, if I want to pick a subset of k columns, I can generate uniformly distributed random numbers 1 through n. I can distribute a random integer in the range 1 to n. I am assuming you all know how to generate random numbers. That is a subject in itself. So, if I am picking all the columns with the same probability 1 over n, 1 over n, 1 over n, 1 over n, I can still pick repeatedly k columns. This is without replacement. If I am sorry, with replacement, with replacement. So, I pick a column and note it, but the column still remains as a part of A. I am going to pick the one of the columns again, that the potential for the same column to be picked. The probabilities are fixed because the number of columns remains the same because I am sampling with replacement. If I sample without replacement, the number of columns waiting to be picked decreases, the probability changes in time, and that provides complications in computations. So, to simplify, we assume we are going to sample with replacement. There are two strategies. One is to sample with a uniform distribution, another one is to sample with called importance distribution. Uniform distribution essentially tells you if the effect of each of the columns are going to be the same, then I do not have to have any preference, I can pick any column from the uniform distribution. But given a matrix A, not all columns have same effect. Why? Given a vector which is a column of A, the length of the vector is a measure of the energy in the vector. We have already talked about that. So, some columns may have larger length than other columns. So, I am going to have to define the importance of columns based on the value of the norm or square of the norm. So, this sampling which is decided by the energy in the vector is the concept that underlies what is called importance sampling. That means, I am going to distinguish the importance of vectors that I need to pick based on the total energy in that vector, the energy measured by square of the 2 norm. So, the sampling probabilities can be based on square of the 2 norms of the rows or columns. In some problems I may have to select rows, in some problems I may have to select columns. Even though in the particular problem under consideration I have to select columns, there will be other areas where I have to select rows as well. So, I would like to be able to select rows and columns based on the energy which is the 2 norms of the rows. The another way would be to look at the leverage scores which reflects the relative importance of the columns. So, what is a leverage score? It again goes back to least squares theory, You remember, if I have a matrix Z is equal to H of x, I have a projection matrix PH that is equal to H transpose, H inverse, H transpose. So, I got the fitted value Z hat is equal to PH of Z. So, this is the vector, this is the matrix, that is the vector. So, I am going to look at the ith component which is the Z hat of I. Z hat of I is the inner product of the elements of the ith row with the column vector Z. There is a diagonal element, please remember P, this is a square matrix. The diagonal element of this is PH III, PHII, Zi multiplies the ith element. So, the influence of the ith observation on the ith fitted value Z hat I. So, if PHII is large, the diagonal element, the ith diagonal element of the projection matrix is large, the input vector affects the fitted value, it has a more influence. If the PHII is small, the input data has a lesser influence on the fitted value. This influence is called the leverage score. To have a leverage, I have a leverage over U means I can control U. So, this Zi controls the fitted value, or to look at in other words, the sensitivity as measured by the derivative of Zi with respect to Zi is PHII. And what does this sensitivity tells you? If there is an error in Zi by epsilon, I can predict how much that error in Zi is going to be reflected in the error of the fitted value. Sensitivities are measured by partial derivatives. So, this sensitivity factor, which is the ith diagonal element, which relates to the impact of the ith observation, the ith fitted value, is called the leverage score in statistics. So, you can measure the importance of a column either by the 2 norms of the column or by computing the leverage scores that reflects the relative importance of the column, That means, PHI tells you the relative importance of the role of the ith column of H in trying to decide the fitted value in the least square fit in model building. So, I can pick the columns based on these 2 quantities. Computing the leverage square is not easy, we had to compute different things, but square of the norms can be readily computed. So, using these 2 methods, we have a sampling procedure for picking the columns of A. The earliest method for randomized column selection is due to Fries, Kannan and Vempala, 1998. 1998 compared to the analysis of linear algebra is almost like yesterday. So it's hardly 25 years old. This is the earliest idea. That means the subject of randomized linear algebra is about 2.5 decades old. It's very new compared to many of the other results in linear algebra. This FKV 1998, they were they were the earliest to talk about the column selection algorithm based on the square of the norm of the length of the square of the norm of the columns of A. So what did they show? Given A, there exists an integer that depends on k, the rank required, and epsilon, the quality of the error, the quality of approximation, to select B such that the Frobenius norm of the difference, the error in the approximation, is equal to the sum of the best rank k approximation, the Frobenius norm of the best k rank approximation, plus epsilon times the Frobenius norm of A. This result has been extended, even though this result has been strengthened, extended in several directions. The importance of the result is the earliest method. So you can see 1990s were the golden period for randomized approach. Even though the Johnson-Lindenstrass algorithm has been known in mathematics, pure mathematics in the 80s, the importance of data science were recognized only in the early 90s. Once the importance of randomized approach using random projection, people started working on various classes of algorithm. One is selection based, another is projection based. The selection based column selection using importance sampling based on square the norm of the columns of A is due to FKV 1998. So they proved this classic result. They showed that using the importance sampling based on the square of the length, I can achieve an approximation whose error is bounded by the sum of two errors. And this error is given in Frobenius norm. So just like I have norms of vectors which are 1 norm, 2 norm, infinity norm, p norm, there are also norms here. X is a vector. Norms of A is a matrix. The norms of A, I have a 2 norm, 1 norm, infinity norm, and a Frobenius norm. So there are several norms. Of all these norms, the 2 norm is called the spectral norm, and the spectral norm is the smallest of all the norms of A. Smallest of the norms of A. Therefore, in mathematics there is always a pressure for the theorist to prove results using 2 norms, but sometimes proving results in 2 norm may be difficult. Proving results in the weaker norm F may be possible, Frobenius norm may be possible. So you go for the low hanging plum, as they say. So if you can prove the first result using Frobenius norm, you strike new ground, and that's exactly what FKV did in 1998. Once they showed a path, there are lots of people who've come down after that to be able to improve these results. Rudolphson and Verschainen in 2007, using the same sampling method, they proved similar results using 2 norm. As I told you, 2 norms are the smaller of all the other norms. So if I can provide an upper bound which is based on the smallest norm, you get the strongest possible error bound. So this is an improved result from here. This improvement came about a decade or so later. And these kinds of things happen in mathematics. When you are trying to prove any result for the first time, you don't have to worry about the strongest possible. You want to cut a new path. If you can cut a new path and get a new result, that provides pathway for others to follow to improve the results, and this is replete in mathematical literature. So 1998, 2007 is very recent. Another paper, Deshpande et al., 2006, they also showed a bound which is very similar to this. B is an approximation. The Frobenius norm of A minus B is related to 1 plus epsilon times the Frobenius norm of the best possible approximation. Best possible approximation. Please remember, in here epsilon multiplies the Frobenius norm of A. Here 1 plus epsilon multiplies the Frobenius norm of the difference between A and best approximation. So this Frobenius norm result is an extension of this, and this is further improved by proving bounds in the tuna. So you can see the pathways that different people have followed. So if the error is less than sum of two terms, you want to be able to reduce the upper bound. They reduce the upper bound to 1 plus epsilon times the best approximation. Then they further reduce the upper bound by replacing the Frobenius norm by 2 norm. I am just trying to talk about the pathways. The details of the proofs are very interesting, important, and by going through the proofs of this, you get a good ability to prove results relating to matrices, probability theory, probabilistic argument using matrix type of argument. Please understand, research is an imitation game. You understand some of the methodologies earlier, then you can combine the tools that you have learned from the earlier methodologies to strike newer grounds. So understanding the derivations in the older methodology is very fundamental to extension. So I have given you a very good idea about obtaining a fixed rank approximation to a given matrix using sampling probabilities. The sampling probabilities are proportional to the square of the norm of the columns of A. I am going to further specialize these things as I go further. I am coming top down. So far, what is that we have accomplished? We talked about problems of randomized linear algebra. We said the essence of approximation relates to capturing the action of the range space. Recognizing approximating the range space is the key to achieving what we want. We said that there is a two-step procedure to achieve that. One is the randomization, another is to reduce the size of the matrix and then do the classical approach on the reduced matrix. The reduction, sometimes we are interested in reducing this, sometimes we are interested in reducing the dimension, sometimes we are interested in reducing the rank. So far we talked about low rank approximation to a full rank matrix. This low rank value k decided by as a function of the singular values, conditioned to the knowledge that singular values decrease very fast. Therefore, the larger singular values do not have much information. It is the smaller singular values do not have much information. It is the sum of the larger singular values that is helpful to capture the action of A, and that is what it was based on. Now, I would like to bring the notion of the second type of approach, dimensional reduction. Please understand, there are lots of two things, a two-stage procedure. The first step is randomization, second step is deterministic. Second step, depending on the problem, you have to pick one of the best known algorithms from linear algebra, which is already done. So, I am not going to concentrate too much on the second step. So, randomization concentrate on the first step, not the second step is not important. The first step is getting that randomized randomization. That randomization can be obtained by one of column selection, another one is dimension reduction. So, that is what I am going to provide an introduction to. So, using the random projection by Johnson, Linden, Strauss in 1984, they developed the theory of what is called L2 embedding, which we already talked about. Given a set of n objects in a larger dimensional space, how do you embed them in a smaller dimensional space where I cannot keep the L2 distance. L2 distance means what? The 2 norm, the 2 norm ui minus uj. You remember, let me rewrite that. You are going to have the distance ui minus uj, the 2 norm. This is called L2 distance. Why this is called L2 distance? Because this is called the 2 norm. L2 is a very technical term. I am not going to go into the details of L2, but for the sake of this understanding, it is enough to understand that L2 relates to the use of 2 norm. So, you can have L1 embedding, L2 embedding, LP embedding, L infinity embedding. For each type of norm, I have a different type of embedding. Each embedding measures the distance in a different way. We have already shown the norms are equivalent. So, without loss of generality, we can attempt to get the L2 embedding function first. Of course, we cannot derive L1 embedding as a special case of L2 embedding. These are all different properties, and there are very good results on L1 embedding, LP embedding, and so on. That is a topic of great interest within discrete geometry. Why this is called discrete geometry? Because I have a collection of n points in M space. The space is large, the number of points is small. I want to be able to understand the geometric arrangement of objects. So, there is an area of mathematics called discrete geometry. Discrete geometric problem deals with this. L2 embedding in discrete geometry, L1 embedding in discrete geometry, these are interesting areas that data scientist borrows from these areas to be able to solve problems of interest in here. Please understand, the title of the course is Mathematics for Data Science or Mathematics of Data Science. So, I am trying to provide the mathematical areas that have impact on data analysis. So, dimension reduction started in 1984. It was imported, the ideas from dimension reduction were imported into the data science areas in the early 90s. Early 90s was also the period where random sampling based on importance sampling based on the square of the length was introduced. So, you can see the two approaches, random projection based approach and random sampling based approach were used in data science starting in the 90s. So, what is the summary so far? Stage 1 is realized in one of 3 ways. One is to be able to sample in the original space, get the random sample y in the range space, and y is expressed as a times omega, and you then process y by doing an orthogonalization procedure on y. We have already illustrated that. Second is the importance sampling by FKV, algorithm 1998. Then the random projection approach, it is somewhat similar to the one that we already talked about in the Lindenstrass algorithm. This also mathematically was introduced in the mid 80s, came imported into computer science in 1990s. So you can see 1990s were the golden period for germination of many fundamental concepts in randomized approach to linear algebraic problem, and linear algebraic problem are germane to solving large scale data science problem, and hence the importance of randomized algorithm in data science. Now I am going to go into details of the sampling based randomized algorithm. How do I design the randomized algorithm sampling based? We have to get into the nuts and bolts. So far I have defined the basic framework for randomized linear algebraic problem. This is a beautiful way to look at the method of randomization in linear algebra top down. Top down. So sampling based, let X be a random vector. So I am going to now go back to several facts from probability theory just to quickly remind you. If X is a random vector, its expected value is also a random vector. When I have a random vector, I have two things. X is a random vector. I have what is called the covariance of X. Covariance of X is equal to expected value of X transpose, which is, then we have talked about the total variance of X, which is equal to the sum of the variance of Xi, and this is equal to trace of the covariance matrix. We have introduced to the notion of trace. The covariance matrix is such that the diagonal elements are all the variance of the individual components. The sum of the diagonal elements is called trace. The sum of the diagonal elements also represents the total variance in the vector X. So given a random variable, I have a mean and variance. Given a random vector, I have a mean, covariance and the total variance. Instead of calling total variance, I simply call it variance. So the variance of X is equal to expected value of the square of the norm of the difference between E and X and E of X. This can be talked about, this can be rewritten as an inner product of the vector X minus Ex. Please understand, subtracting the mean is called centering. So this is called centered vector, centering. So this is the vector, I am sorry, the transpose is the row vector, this is the column vector, so this is a scalar. Expectation, this is the sum of the squares. Expectation of the sum is the sum of the expectation. Sum of the expectation of the variance of the individual component, that is a total variance. So that is the covariance matrix, and the variance of X is equal to the trace of the covariance matrix. These are all fundamental facts that come from basic probability theory relating to vectors. Here I have illustrated how to compute the total variance, the covariance matrix and so on. So it is a combination of this and that you need to be aware of. Now I am going to talk about the first randomized algorithm to solve one of the simplest problems in linear algebra, namely matrix vector product. A is a matrix, V is a vector. My job is to be able to compute the matrix of the vector, and we all know computing the matrix by a vector can be thought of as computing the linear combinations of the columns of A with the components of the vector. So AV is a vector which is simply the linear combination of the jth column of A with the jth element of the vector. It is the sum of n vectors because the constant multiple of a vector is vector. So sum of n vectors. So now AV is the exact value. So, here I am trying to add all the multiples of the column. In approximation, I am not interested in the sum of all the columns, I am interested in the sum of some columns. If I am interested in adding only some of the columns, the linear combination only some of the columns, it will be an approximation to the exact sum, and I would like to be able to pick the column and the probability such that the approximation is a good approximation and the computation time is less. Please understand, there are two key things. One, I should be able to compute fast. Two, I should be able to compute whatever I am computing fast to a good quality. So, AV can be estimated using a sample of columns of vectors of A. That's where sample comes in. Why sampling of columns is important here? Because the matrix vector product is simply computing the linear combinations of columns of A. The vector V is given, columns of A are given. So, if I can select a subset of columns from A and multiply them by the corresponding elements of V and compute that partial sum, and that is a good approximation to the total sum. The error in the estimate is measured by the variance of the estimate. The estimate is going to be a random variable because I am going to use randomized algorithm. If I am going to compute estimate and the estimate is a random variable, I have to go back to basic statistics, the quality of estimation. You remember that? We did it in previous modules. We talked about the quality of estimates. It must be unbiased, it must be efficient, it must be consistent. Efficiency deals with the variance of the estimates. Unbiasedness tells you that the sampling distribution is centered at the unknown mean. So, I would like to be able to approximate where the estimate is a good estimate, good in the sense of variance being less. Please understand, efficiency of the estimate relates to the variance of the estimate. If I have two estimates, one with a lesser variance than the other estimate, the one with the lesser variance is said to be more efficient, and that is the definition of efficiency in estimation. So, there are two ways to sample the columns of A. One is the uniform distribution, another is the importance distribution. Sampling from uniform distribution is called uniform sampling. Sampling from importance distribution is called importance sampling. I am now going to do a motivating exercise to help us define the probabilities. So, what is the whole idea here? The columns are there. Uniform distribution is all 1 over m, but not all columns. So, if the columns of A are normalized, all the columns are equal length, then there is nothing much to distinguish between them. Uniform distribution is the best approximation, the best distribution to sample. But I was given the raw matrix A, nobody did any normalization on the length of the vectors. So, the length of the vectors without normalization differ. The square of the length of the vectors determine the energy in the vector. So, I would like to be able to pick important columns based on the amount of energy contained in those vectors, which is measured by the square of the norm of that vector. That is the basic idea. So, I am going to motivate by a simple example. This is a case of data dependent sampling. So, let x be a random variable. Let us assume it is a discrete random variable. This discrete random variable may take the value ai by pi with a probability pi. So, this is the problem motivating. I am going to work with a simple example. Sum of pi is 1, and to make my calculation simple, let us assume 2, n is equal to 2. So, I have a1 by p1, a2 by p2, p1 plus p2 is equal to 1. X takes the value a1 by p1 is the probability p1, a2 by p2 with the probability p2. Therefore, the expected value of x is a1 by p1 times p1 plus a2 plus p2 times p2 is a1 by a2 is a bar. A bar, A1 plus A2 is the exact value. So, the estimate is exact. So, originally the random variable x happened to take value A1, A2. I am going to pick A1 with a probability P1, A2 with a probability P2, but instead of picking A1, I am taking a value scaled by P1. So, I am transforming A1 to A1 by P1, A2 by A2 by P2. If A1 is random, A1 by P1 is random. If A2 is random, A2 by P2 is random. So, x is a random variable whose sample values are Ai by Pi, which is picked with a probability Pi, summation Pi is 1, and in the case of n is equal to 2, expected value is given by A1 plus A2, which is A bar. And what is variance of that? The sample value minus expected value square times P1, the sample value minus expected value square times P2. If you simplify and do the algebra, which I have given everything in greater detail, you expand, you collect the like terms, you come back and verify that the variance of x, the variance of the scaled value of x, please understand, originally x took the value of A1, A2 with a probability P1, P2. So, I am transforming the variable by dividing by the probability Ai by Pi. The transformed random variable is such that its mean is A1 plus A2. Its mean is A1 plus A2. So, here I am computing the variance of this random variable x, which is A1 square by P1 plus A2 square by P2 minus A1 plus A2 whole square. Now, if P1 is equal to P2 is equal to half, that is called uniform sampling. In the special case, expected value, look at this now, A1 by half plus A2 by half is equal to 2 times half, times half, that is equal to A1 plus A2. So, that is expected value when P1 is equal to P2 is equal to half, uniform distribution. When you do uniform distribution, this is 2 A1 square plus 2 A2 square minus A1 plus A2 whole square, and that is equal to A1 minus A2 whole square in the special case. So, the variance is always greater than 0 so long as A1 is not equal to A2. So, under the uniform sampling, the variance value is essentially A1 minus A2 whole square. Now, I am going to find a new sampling probabilities P1, P2 such that the variance of the random variable x is less than the one that will obtain from the uniform distribution. If I can show there exists a distribution for which the variance of x is less than the one that obtained by uniform distribution, this new distribution, which is not a uniform distribution, is better from the perspective of being able to estimate random variable x, that idea. So, for what choice of PIs will the variance be minimum? Please understand, the variance has two quantities, one that depends on P's, the second one does not depend on P. P is the only control variable. So, minimizing the variance is equivalent to minimizing the first term. So, what is the choice of Pi that will minimize the variance? That reduces to minimizing A1 square by P1 plus A2 square by P2 when P1 plus P2 is equal to 1. So, the minimization problem under constraint. I want to be able to find optimal P1, P2. So, the problem of trying to find the best distribution now reduced to a constraint minimization problem, which can be readily solved by Lagrangian multiplier method. Go back. I am trying to use many of the results that I have done in the previous lectures in here. That is the beauty of this. and hence the importance of the earlier part. So, I am trying to define a Lagrangian, I am trying to define a vector P which is P1, P2, I am trying to define a constant lambda which is a Lagrangian multiplier. So, Lagrangian multiplier lambda is a real constant. So, I have a 3 variable problem P1, P2 and lambda. This is the original objective function, this is the constraint, lambda times the constraint. I compute the partial derivative with respect to P1 equated to 0. I compute the partial derivative with respect to P2 computed to equated to 0. I get an expression for P1 square, I get an expression for P2 square. We do know I have to impose the condition P1 plus P2. P1 plus P2 now reduces, when I combine this with the Lagrangian multiplier condition, that gives rise to A1 plus A2 must be equal to square root of lambda. So, if I substitute it for lambda in terms of A1 plus A2, I get the optimal probabilities to be A1 by A1 plus A2, A2 by A1 plus A2. This is called P1 star, this is called the P2 star. And if I substitute the value of P1 star and P2 star in the variance expression, I get a quantity which is now look at this now, A1 plus A2 whole square minus A1 plus A2 whole square is 0. I have reduced the variance to 0. So, this is variance reduction. So, this reduction of variance from uniform sampling to specialized sampling PI, and what is PI? PI is related to the P1 star, P2 star, they are related to the value that X was originally taking. So, originally X was taking a value AI with a probability Pi. Now, I sample A and normalize it, the value by Pi. This is the, I should not say normalize, scaled. I scale it by the probabilities. I now shown that if I scale it by probability and choose the probability in a particular way, I can compute the samples. I can compute an estimate whose variance is minimized. I hope you are with me now. I wanted to bring in the basic idea of the concept of minimum variance estimation. Please understand, whenever there is a random quantity, I want to talk about the probability of a random variable taking values in an interval. I want to talk about the expected value. I want to talk about the variance. I want to talk about the unbiasedness of the estimate of X. I want to talk about the efficiency of the estimate. So, now you can see linear algebra, probability theory, statistics all coming to you to be able to solve problems in randomized linear algebra, and that is the beauty of data science.